let's just wait for a few minutes because I'm not seeing any students who have joined. I'm seeing that so far nobody joined. I'll wait for further few minutes, then I will start. Okay, so let's start today's session. Um, Looks like today's attendance is quite low. Anyway, uh, as usual, we will keep it more interactive. Okay, let's start. So, this is the problem solving session for the week number 4 lectures, and this is actually a problem solving session for the NPTEL course Thermal Physics, and the instructor of the course is Professor Debamalya Banerjee. And so we'll so today's problems that we will discuss and that we will try to solve is based on lectures of on week number 4, and that is basically the Brownian motion. And So I actually do my research in active Brownian particle, and so although this Brownian motion, the interest of this topic why was like nearly 100 years ago, basically like 120 years ago, but uh, there are 1905 Professor Einstein published three groundbreaking papers. uh, Out of those three, two you probably heard. One of those three papers is on photoelectric effect, for which Professor Einstein got Nobel Prize, and another one which is on special relativity, that also opened a certain wide path that actually was followed by giving the theory of general relativity, and goes on. And the photoelectric effect actually was one of the pillars for quantum physics. But the people call it, the scientists call it the three sisters, but three twin sisters. But this third paper, which was on the Brownian dynamics, where he established the relationship between diffusion coefficient and this microscopic movement. So there was sort of a relationship between a microscopic parameter with a macroscopic parameter, which is diffusion. But it was neglected. It was neglected because that was the era of quantum physics, and also side by side people were more interested in relativity, but because that idea was quite fascinating or groundbreaking. But always there are few scientists who were working on this Brownian dynamics, or people then called it sort of the proof of molecular approach. So people 120 years back, people didn't believe that all of these things are built of atoms or molecules. So there are two sections of the people. One was people who believed in atomic theory. They were called atomistic. And people like Oswald and all those things who do not believe in this kind of molecular motions and all these things, or people didn't believe that molecule exists, those were called non-atomistic people. But later on, as science advanced, it became apparent that atomistic theory or atomistic concepts were right thing. So I am just giving this context, because so that you can appreciate that sometimes a research topic or sometimes a concept which can be neglected in certain generation, but later on it can open a variety of plethora of avenues to explore. But side by side, people were first Einstein was so much adamant, and nowadays people are you know fascinated by giving some theory based on mathematics. But sometimes those things are not uh, what should I say, that those things are sometimes are just from the beauty of mathematics, not that much represents any physical significance. But people like Einstein, whom scientists consider as one of the, I think it's the biggest theoretician in our current scenario on 200 years or 300 years. He believed that if someone could get the experimental verification of this Brownian motion, or this the relationships, the d by kpd by 6 pi eta a, that could actually uh, settle a debate on this atomistic and non-atomistic group of people. And later on, it evolved, and nowadays it is people calls people call this era, like this early 2000 to right now, this era of active Brownian dynamics or active dynamics. So you can see lots of scientists in physics, or chemical engineering or engineering, mechanical engineering, they are doing lots of research in this field. But the basic understanding or basic pillar was built in this decades, 19 20th century, in the beginning of 20th century, and this so that is the thing. So let's start the, all of you probably know about this Brownian motion, because you have probably seen also, like if you dispersed some colloidal particle, you guys some of you guys perhaps don't know what is colloidal particle, but if I give you some example, you will understand it. Let's say you disperse some pollen grains or some molecules which size is big compared to the solvent they are in. So they are nearly a few micrometers to few nanometer, like 100 nanometers or 200 nanometers. So they actually show some kind of zigzag motion, and the name Brownian motion is given because there was a biologist, Brown, who actually first observed this phenomena when he saw that pollen grains are moving in in water. So this is the main pretext of these things, but later people theorized these things and got the physics, because physics comes from the fundamental principle. So they tried to give the theory. So this is this. So let's just start today's session, because I'm not going to discuss about the lectures, because I think and I believe Professor Banerjee has given, or the lectures he is putting on the NPTEL website, that are quite good. So there is no need in repeating those things. Rather, we will focus on problem solving session, so that we can get the ideas what the theory is, or what the lessons are uh, saying, so that we can solve some problems, and we can see, okay, so these things are meant for solving these things. Okay, so let's start. So before beginning, there are one announcement I want to do. Last week, actually, there are some technical problems, because there was a load shedding or power cut in from my side. So that's why some network issues was there. But do not, you don't need to worry about these things. I am recording all these things. You will get it. But I will suggest that please be patient and please join, and please remain in that link. I will join somehow. And one thing that some girl probably was saying, that there was some problem in accessing the videos. I think that was not problem from my side, that was problem from her side. So does anybody uh, face the same problem, or is anybody facing the same problem, or accessing the videos, or all of you guys can access the video? Please write in the chat box, or unmute yourself and tell me whether you can access it or not. Ranganathan?
Sir?
Yeah, so you can access the YouTube videos, right?
Yes, sir.
Okay. Okay. So that's great. Let's start. So the uh, okay. So the first problem that says in which case the motion of the Brownian particles is greater. Option A, higher temperature. Option B, higher viscosity. Option C, higher size of the particles. Option D, all of the above. So anybody who want to volunteer to answer these questions? Okay, let me give um, some hints and then again we'll try. Okay. Okay, so according to the Brownian motion,
Sir, higher temperature.
yes, yes, Ranganathan, please tell me.
Sir, the first one, higher temperature.
Yes, so if the viscosity is higher, then what will what 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 will it happen then? Anyway, Ranganathan is absolutely correct, but we will deep down this thing. So let's say x, we are talking about the movement of x. X is, let's say, positions. Okay. Now, if you see, and let's say starting position is x naught. For Brownian motion, I will denote it as Bm. The average of this quantity, which can be written as this delta, the displacement's average, is 0, right? But this one, square, this is 2dt. In general, it has been written as 2n dt, where n is the dimension. Since we are talking about one dimension, there n will be 1, so that's why this 2 dt. Okay. Now motion is higher means this quantity is higher, right? Motion is higher means, because the average is 0 for any quantity, so that will not give me any clue about the motion. So to get some idea or to quantize the motion, quantize means to quantify the how much is moving, we have to talk about this thing, this mean square displacement. And this mean square displacement, how does it, this is square displacement, so mean will be the average of the root of this thing. So this displacement square is varying with 2 dt, where d is diffusion coefficient, t is time lag. People also write it as time lag. So since you know that for Brownian motion absolute time doesn't matter, so it does matter where it starts, it doesn't matter, it does matter with the time interval it undergoes. Okay. Now, so the question is, if the square displacement is higher, then their motion will be greater, right? Are you agreeing with me in this thing? Ranganathan? Yes, yes. So now, so if to compare, then we have to talk about this thing 2d tau. Now tau, if tau is fixed because we are talking about only the macroscopic variable. Tau is fixed because we are since we are comparing the motion of the Brownian particles, we have to fix the tau, the time lag. Only quantity is d. D is the diffusion coefficient, and its formula is kBt by 6 pi eta a. People also write in terms of this RT 6 pi eta a n by a. Since you guys have done 3 other session of problem solving, so you know that AR is equal to NAKB. We just use this factor, use this thing. Now, so far we have established that motion will be higher if D is higher. So motion is varying with D. If D increases, motion increases, right? Okay. Now, then our problem becomes how D increases. Okay. Now, in the expression, Kb is a constant, pi is a constant, 6 is a constant. Only variable is T, temperature. First, temperature, which is T. Second, viscosity, which is eta. And third is size of the particle, which is called radius. Here radius of particle. Here all here in all the discussions we are considering spherical particle. There is only one characteristic length scale of the particle, which is A. Now, given this expression, if T increases, D increases, because this is the linear relation, T varies as T. So this will D varies as T. So this will increase. But D inversely proportional to eta. So this will decrease. When eta decreases, D increases. And radius of particle, which is A, that is also inversely proportional to size of the particle. So that is also inversely proportional. So higher temperature, so if the temperature is higher, then the diffusion coefficient will be higher, then the motion of the Brownian particle will be greater, right? This is correct. Higher viscosity, no. If viscosity increases, then diffusion coefficient will decrease. So the motion of the Brownian particle will also be inhibited, right? So this is not. Now, if size of the particle increases, the diffusion coefficient decreases. So higher size of the particles, that means diffusion coefficient decreases. That means motion of the Brownian particle is diminishing. So this option. So option A is correct. Higher temperature. Okay. So the point is clear. Any doubt so far? Any questions? Any doubt?
No.
Okay, good. Ranganathan says no. Let give others some chance. so that they can, you know, they can ask their queries. Jaga Jaga, Sham, Renuka Devi, Perumal, Kirtiga. Excuse me. So it's okay, right? Okay. Since there is no questions, mm, so you guys can ask that why viscosity, when viscosity is increasing, diffusion decreases. You could ask that, right? So the concept of this thing is when viscosity increases. What is viscosity? Viscosity is a property of the media which prohibits or which actually resists the motion of the bigger particle or the macroscopic particle. So here when viscosity increases, the media in which the colloidal particle or Brownian particle is in, that uh, will not move as much as it can move in a lesser viscous media, right? So let me give you one example. There is water whose viscosity is much smaller than the viscosity of glycerol. Now if you see, they if you know put some particle in glycerol solution and in water solution, what do you expect in which the movement of the particle is higher, glycerol or water? Anyone? Anyone? It will be water, right? Since this is less viscous. Okay, so let me proceed to the next problem. So next problem says, in terms of Brownian movement, which of the particle will have the largest motion? First option is motion of pollen grains in still water. Option B, motion of dust particles in a room at normal temperature and pressure. Option C, diffusion of calcium through bones. Option D, motion of atoms in solids. Please tell me the answer with reason. All of you guys have seen Brownian motion, right? Practically, and seeing the videos that Brownian motion is happening. All of you guys have seen or not? Please give me the answer that what will be the correct option and with explanation or reason. What do you think?
I think D option, sir.
Option D, that motion of atoms in solids. Why so? Why so? Give me the reason, or what are you thinking to give that option D, which is motion of atoms in solids, is correct option? Why are you thinking like that? Who answered it? Probably.
For myself, sir,
Yeah,
I
please.
think
He's
motion of atoms in the solids only having the largest motion, sir. Compare that, I will imagine. That is
no.
correct or not? I don't know
Yes,
exactly, sir.
that's actually absolutely fine. But I'm saying, why are you thinking like that? There should be some, you know, concepts, or there should be some thinking. Because okay, see, solid does solid flow. Solid doesn't flow, right? Whenever we are thinking about solids, we think about the lattice points. They are all the molecules are at certain lattice points, because solids here, solid, liquid, gas, here we are thinking it as, sort of media, right? Now when they are in solid, the molecules of that solid are fixed at certain lattice points. They just vibrate, so they are actually creating a cage. So whenever a atom will be there in solid, it will be caged in certain space, so that will not move a great deal of distance. It will be caged at certain point. Okay, so anyway, thank you for responding. That is what all I want. Okay, anyway, thank you, Renika Devi, for the answer.
Thank you, sir.
Yeah, so we have seen, let's say this y-axis is msd, this is tau, which is time lag. For Brownian motion, people have seen this is a straight line with a slope. So msd versus d, this is, let me write square. Excuse me. So if you take this thing, so this is this thing, so this slope will be 2d. Okay, now for solid with same viscosity, this will after certain characteristic time, its msd will be like this. This will give you a plateau region. What does it plateau region means? That after certain time, the displacement is not growing, it is fixed. That is what I was referring to as cage thing. When something is in cage, it cannot escape the cage, because there will be some boundary. So this is, and that's why this, plateau region is happening. This is associated with the elasticity of the media. So that's why, Renuka Devi, motion of atoms in solids will not produce the largest motion. This is not possible. Similarly, diffusion of calcium through bones will also not give, because bones are quite elastic, right? Let's say if you are seeing this kind of a bone, so this will be confined in this kind of region. It can only flow in this region. There will be some this thing. This is also not possible. Motion of pollen grains in still water and motion of dust particles in a room in normal temperature and pressure. These two can be comparable, but it depends on pollen grain size and dust particle size. So let's say dust particle size is much larger than most pollen grains, then this will be the correct answer. But when you are talking about dust particle, let's say gold dust particle, whose size in let's say nanometer border, then this will be higher. So here the question is some kind of dubious thing. So generally, if size of pollen grains smaller than dust particle, so option A is correct. Otherwise, not otherwise, if dust particle, let's say A dust is greater than A pollen, then option B is correct. We are considering viscosity. A greater thing will be check with eta times A, this quantity, because temperature is fixed, let's say. So this eta times E, if this product for whom this is greater, movement will be lesser. So in that's why this question is not, there is some is not clear. There is less clarity about the questions, but we can conclude like this. Okay, so this is the thing. Okay, so third question says the ratio of Avogadro's number as measured by Jean-Baptiste Perrin and modern day accepted value in a modern, let's say the ratio is R, which is Na Perrin by Na modern. So what will be the answer? This is quite informative questions. I'm not expecting all of you know this answer, but if anyone knows, please unmute yourself and then respond. Just to in the meantime, you guys please think, or if someone knows, please raise your hand or unmute yourself and answer. I'm just giving you an idea about Avogadro number. Okay, let's say you are counting 1 billion, let's say 1 billion of particles per second. Okay, so you just tick, you have counted 1 billion number of particles. To count Avogadro numbers of particles, it will require nearly 2 billion years. Do you know what is the age of the Earth? Do you know what is the age of the Earth? This is nearly about 3.8 billion years ago. So half of the this thing will, half of the edge of the earth will be used here. But that's why science comes, right? It gives you a certain uh, estimation which is closely, matches. So that's why the beauty of the science. Anyone knows, or should I give the answer? Looks like nobody knows. Okay, so Perrin was the first person who actually Perrin was the first person who actually gives, or who actually first saw the diffusion, this thing that actually gives, that actually establishes the Einstein's claim. So when he actually, how does he calculate this thing? What he does, he took bunch of particles, 10,000 particles, okay, 10,000 particles, and he actually gets their displacements, and then actually got this mean square displacement, which is 2d tau. Then since he knows this displacement 2d tau, so this d will be this displacements divided by 2 tau, and this relation actually gives you RT by 6 pi eta a. So all these things are known. He have to calculate this thing, so that's why he could actually RT by 6 pi eta a times 2 times. So he first attempted to discover the Boltzmann coefficient, and then using this thing, when he knows this is also kb t by 6 pi eta a, so here he gets the value of kb, and he knows because the universal gas constant R value was already known at that time. So he divided this to get Na, he just divided R by kb, which he got from here. So in that way he got the value, and this value was something 7.1 10 to the power 23, this kind of value. And what the modern day value? Modern, this is 6.023 10 to the power 23. If you take the ratio, this is greater than 1. So option D is right. Okay. Okay. So let's proceed to the next problem. Next problem says the pressure at sea level at 27 degrees centigrade is 101325 Newton per meter square, which is atmospheric pressure, right? Now at a certain height, the pressure is 1 by 16th times the pressure at the sea level. Okay. If the temperature is increased 4 times, then what is the pressure at that height? Do you know how to solve it? Anyone? Then I will wait for 1 or 2 minutes. Otherwise, I will give some hints, then I will wait for 1 or 2 minutes so that you can solve it. The question is understood, right? To all of you guys. Question is well understood, or should I repeat it? Anyway, you can see on the screen. First, we have to get since there is height involved, first we have to get how pressure varies. How pressure varies with height. Okay, so let me give you some this thing. You all of you know, huh? This gas equation, from the gas equation, that P is equal to N K B T. N is the number density, P is the pressure, right? So P varies as N, right? Now, as the number density increase, pressure will also increase. So now the number density means how many number of particles or molecules, gas molecules will be there. That actually, let's say N1, let's say this is sea level, this is C, this is Z0, and this is the height, this is Z. If here it is N1, sorry, N0 and P0, and here it is N1 and P1, N1 is N0 times potential at V1 minus potential at V2, potential energy, divided by, sorry, V2 means V0, here V0, divided by kBT. Now here, because since there is height involved, there is some potential gradient is there, right? Now which potential is there? Since there is height, there is gravity field, right? So this energy will be, this energy, potential energy will be gravitational energy, right? Gravitational potential energy at Z, height Z, which is mgz, right? And V0, similarly V0 is mgz0. And this equation actually says, this distribution it follows is Boltzmann distribution. I hope you guys are following me. Now if P linearly varies with N, then this we can write in terms of P the same equation, right? P1 will be P0 times, let's substitute this thing, mg z minus z0 divided by kBT. So far it is clear, right? So this is the equation. Okay. Now the question says, at what P1 at Z is P0 by 16. Just put it here. When you will put it here, then P0 by 16 is equal to P0 times exponential, let's minus, keep it here, mg z minus z0 divided by kBT. Then what will be, this will be cancel out. So this will give you exponential of minus mg z minus z0 kBT will be 1 by 16. This expression we got, right? Okay. Now if temperature is increased 4 times, then what is the pressure at that height? Now this temperature, this guy will change to T prime. So what will be the new pressure? P prime will be P0, similarly exponential minus, okay, mg, okay, z minus z naught divided by kb T prime. And how this T prime is connected to T? This is T prime is 4 times T. I will substitute this here. Let me add some. Let me add just a minute. Yeah. So far it is clear. What we are trying to do is, we know that pressure linearly varies with number density, and the number density follows Boltzmann distribution. So pressure will also follow the Boltzmann distribution because that's just linearly varying. Now, how the Boltzmann distribution is varying? This is, there will be exponential minus V1 by V0 by kBt. V1, V is the potential that the particle is in. Now this is, since these are gravitational field, the potential will be gravitational potential energy. So there will be mgz, mgz, right? Now after some calculations we got, since this is pressure at height z, is the pressure at is 1 by 16th time at the of the pressure at sea level, then this expression, which is, let me go to this here, put the pointer option. So this expression, you guys can see my pointer? Please respond. Hello. You can see the laser point, right? This one. Anyway, we'll get this expression is 1 by 16, this value. Now we need to calculate what will be the pressure value when this T will be changed to T prime, where T prime is 4 times of T. Okay, so that is quite easy. We will write here. This is P prime, which is P0 exponential of minus mg z minus z naught divided by 4 kb T, because T prime is equal to 4T. Now we can write it is this one. So exponential of minus AB, we can write is like this, right? Exponential of minus A times B, right? So this, we can put this 4 outside. So what exponential of minus mg z minus z naught divided by kbt times 1 by 4. Now we know the value of this thing. This is 1 by 16. So we will make it P0 1 by 16 to the power 1 by 4. Now what is 1 by 16? this is P0 2 to the power minus 4, this is 1 by 4. So this comes P0 times 2 to the power minus 1, that becomes P0 by 2. So it will become the pressure at the sea level, it's half, right? Now what is the pressure at sea level? P0 was 1013, let me see the number. So 101325, so this is 101325, so P prime will be P0 by 2, which is 500662.5, so 50063, so 50063 Newton per meter square. So this is the correct options. So any query so far, any problem with this? I will give 1 minute to think about this and to see the solution, then I will proceed to the next problem. You guys please say just coming in 1 minute, 1 or 2 minutes. Any problem so far? Because this problem is quite important, because if you understand this problem, then there will be easier to solve the other problems. Anyway, since there is no problem right now, I will proceed to the next problem, because anyway I will give some recap at the end of the session. So okay, so this is a quite similar, the basic concepts are quite similar to the previous problem. The problem says, in a vertical distribution of Brownian particles, vertical distributions of means there is gradient field, in the height field there is, the pressure at a height z is 1 1/8 times the pressure at the base. What is the ratio of number density at height z and at the base? So if you understand the previous problem, this is just cakewalk, right? So unmute yourself and answer, because this should be answered. If you understand the previous problem, and if you if you heard the solution of the previous problem, you can answer it immediately. So where in the case of air molecules, those air molecules are also Brownian particles, right? They are moving zigzag and they are doing some Brownian motions. So same thing here applied here. So I want the answer. So unmute yourself and tell me the answer. Muthulakshmi, then Muri, then Muri D, right? Then Muri probably. Sham, Perumal, am I audible? Because I'm not getting any responses.
Audible, sir.
So, okay, great. Then Renuka Devi, you say, or at least attempt it, right? So what should be the answer? If pressure at height z is 1/8 times, then what should be the ratio of number density at height z?
Same for previous problem procedure.
Yes, same thing, right?
Finally, P naught exponential of minus mg z minus z naught by kpt.
Yes, that's true.
Sir, I have one doubt, sir.
Yes, please.
Previous problem given that the value pressure level at some degrees, 27 degrees Celsius, 10,000, sorry, 1 lakh on 1,325, sir.
Great.
That time 1 by 16 times pressure at the sea.
Yes.
The same time the temperature will be increases 4 times, sir. But here given height z is 1 by 4 8 times, sir.
No.
That means
Yes, that's one question. But the problem was different. Problem was that
yeah.
if the height, if the pressure is 1 by 1/16 times, but if the temperature again, they talked about the temperature increased 4 times, but sometimes it happens the temperature doesn't increase in that period. Sometimes it happens, right? So in this problem, since there is no mention of temperature, only pressure varies, okay, due to the height is varying. So in the exponential of exponential of minus mz z minus z naught divided by kbt, t is fixed here, t is not changing, okay. Only thing which is varying is z, right? But here you need not to worry about temperature also, because I have written one thing, that from gas equation, pressure P is equal to nkbt, right? You can see here. Let me this is here. So if pressure is 1/8, then number density will also be 1/8, right? Isn't it? Because in this problem, there is a further addition, the temperature is increased, one other variable T, that is also varying. But in this problem, this is not happening, right? So we know from gas equation P in kBT. So P is varies as N, right? P varies as N, but here P1, so this is again same thing. So how P1 by P naught is exponential of minus mz z minus z naught divided by kBT. Anyway, this will also be n1 by n0, which is 1/8. So this will be the option, right? So this is quite easy problem. Okay.
Okay, sir. Thank you.
Yeah. Only thing is different from the previous thing. The previous time we have to understand that in the question it was given that what will happen if the temperature at that height z is changed, but here there is no mention of temperature change, so we need not to worry about those things. Okay, so next problem. This problem says a gas of molecular weight m is kept in a column of height h and at temperature T. The pressure and number density at the base Z0 is P0 and N0 respectively. At what height the number density falls off as 1 by E? Same problem. So can you tell me at what height the number density falls off as 1 by E? Because the same problem is used here. So I want the answer because the same formula will be used here. This formula, same formula here, same formula here. In terms of here we need to get that n1 by n0 is 1 by E. At what height this expression will be 1 by E. So you equate this, you will get it. So you know these expressions, right? You know these expressions. Have you gone through the lectures of week number 4? Okay, let me write the expression, then you guys can solve. So let's say the height at z, the okay, this is, let's assume. So n by n0, which follows same Boltzmann distribution, Okay. Now in the problem it is given this 1 by E. So all this temperature, pressure, all these things, these are just to give some, to make you guys, sort of think about or sort of misguide you, so that you it to test that you guys understand the concept. Okay. Now if that is exponential, then this power this is exponential of -1. So what is this term here? In the bracket term will be 1, right? So m z z minus z0 naught by kb t is equal to 1. Now m here is a mass of single molecule. We can write as m g z minus z0 divided by r t, because if you remember the previous class we written that r by m is equal to kb by m, because r is equal to kb times Avogadro number and molar mass is equal to m into Avogadro number. Okay. Now just write in terms of this, RT by mg is equal to z minus z naught. So z will be z naught times RT by mg. Okay. So this will be the correct answer, option A. This is quite simple, right? So what we have to do, since we know the number density or the pressure, here since the question is on number density, if now the question says, all the questions are same, just question says at what height the pressure falls off as 1 by E. So here instead of n by n naught, you have to write p by p naught is equal to exponential of minus mz z minus mg z minus z naught divided by kbt is equal to 1 by E, and then you have to do the algebra. Okay. Okay. So let me proceed to the next problem. This problem says horizontal displacements of a Brownian particle in a medium at temperature 20 degrees centigrade in 11 successive intervals of 30 seconds are 5.6, minus 4.7, minus 10.8, minus 6.6, so. Find the diffusion coefficient of the medium. You can do this, right? So you are given the displacement. So what we know? We know the mean square displacement in one dimension is equal to 2 times diffusion constant times time lag. Here time lag is the time interval which is 30 seconds, that is known. So we have to calculate the diffusion coefficient. So first we have to calculate the mean square displacement. Displacements are given, we have to take the square, then have to take the mean of that square displacement, that will give me the mean square displacement. Then that value we have to equate with 2 times d times tau. Tau is given. Then we will know what is d. D will be mean square displacement divided by 2 times tau. So I have to write it like this. So if this is mean square displacement, which is 2 times d times tau. From here we will get d is equal to delta square divided by 2. What is delta? Deltas are 0, 5.6, minus 4.7, minus 10.8, 6.6, minus 9.8, minus 11.2, minus 4, minus 15, 15, 19.1, and 16. Tell me what will be the squares of this thing. This is 0. Tell me, or do this problem. Then you will calculate the square and take the average. So this will be sum of all this thing. So this is 1 by 11, since there are 11 entries, divide, this is sum over delta a square. Delta a is each element of this delta square. So you will calculate this, then equate with this thing, you will get it. So please try it right now. In between I am writing the, I will ask you the answer. Please attempt it, because this is quite simple problem. This is 31.36. What is this average coming? Please tell me what is this average coming. If you take these problem solving sessions and if you try to try to solve this problem in this session, you will get beneficial. I will tell you one story. Last year I was taking one NPTEL problem solving session for one course, that was basic thermodynamics, all this, some course, and one student who was very much regular, and he used to do problem solving every time. So he used to listen to the uh, these things, and he tried to also ask questions and clarify his doubts. And after the course, the problem solving sessions got over, the examinations was done. One day actually he sent me an email that, okay sir, the examinations, the result of the examination is out, and I he was the topper. So that quite helpful, and I don't know whether that was helpful, my sessions were helpful to him, but it was good on from his part that he informed me the result. So what I'm trying to say is you will get benefited from these problem solving sessions, because there will be little bit of little things while solving the problems which will be required in the examinations, right? And sometimes those things are also important to understand the concepts as well, because when you are trying to solve a problem, then you will get the flavor of the concept. Okay, this thing, the theoretical thing.
Sir, I think option A.
Option E means 1.965 into 10 to the power minus 12 meter square per second, right?
Yes, sir.
Yes, absolutely correct. Thank you. Thank
Thank you,
you.
sir.
At least you are responding, and at least you are showing some intent to do those things. That is quite great. Okay, so if you add this for my thing, it's coming out to be, this is coming out to be 261929694 divided by 11 micrometer square per second. Then I got is 117.90. Okay. Now if you take the diffusion coefficient, this will be just this value divided by 2 tau, and this value is known, 117.90 micrometer square per second divided by 2 times 30. This is second. So sorry, this is micrometer square. This is micrometer square. So this will be micrometer per second. And if you do the calculation, this is coming out to be 1.965 micrometer square per second. Now 1 micrometer is equal to 10 to the power minus 6 meter. Just do the conversion. 1 by 10 to the power minus 12 meter square per second. So Renuka, you are absolutely correct. So this is this one. Thank you. Okay, so now this is one simple problem. It says, which statement is the best description of a random walk describing Brownian motion? Option A gas or liquid molecule travels in straight line until its direction is randomized by a collision with another molecule. This is absolute. This sounds just like the Brownian motion, right? Because gas molecules are moving, but when they are collided with another molecule, that will be randomized. The direction will be randomized, right? Option B, a gas or liquid molecule travels in straight path due to an outside disturbance. In Brownian motion, there is no outside disturbance. All the things are happening as a macroscopic object and its media as a whole. So there is no outside disturbance. So option B is not correct. Option C, a solid molecule vibrates in its place. That is also not correct, right? Because that is vibration, that is not Brownian motion. Option D, a gas molecule spins randomly. Now a gas molecule spins randomly, that is also not correct, because it actually resides at a certain place and it's moving, spins. But if you talk about orientational diffusion, orientational Brownian motion, it could be one chance, but that is beyond the scope of this course. So I will not talk about these things. There are different kind of object that shows this kind of thing, but I will not talk about these things. Okay. So far option E is correct, because it is saying something which is actually Brownian motion. When a macroscopic particle, means like in shape and size between some few micrometer to few nanometer, that actually collided with some molecule, and it changes its directions, it randomizes its directions. Okay, so here, since this is theory, so this is correct answer. Now this one also you should answer, because we have discussed about it. It is possible from a study of Brownian to determine the value of Avogadro number. Option B, Boltzmann constant. Option C, both A and B. Option D, none of the above. I discussed with you when we were discussing about the Perrin problem. When there was like ratio of Avogadro number, which what actually calculated by Perrin, and modern day value. So what will be the value? So first, from experimental point of view, we will get the mean square displacement, and in the mean square displacement, that is equal to 2d tau. So from here we will get diffusion constant, we will get diffusion constant. Now we know this diffusion constant d is kBt. So from here we will get diffusion constant kBt by 6 pi eta a. So since if we know if d is measured, then from this relationship kb will be determined. So Boltzmann constant is also correct. So this is one thing. But if you know kb, if you know this, you can easily get the Avogadro number, because what is this? This is R by kb, because R is the universal gas constant, you know. Gas constant, you know. So from here you also get to know the Avogadro number.
6.023, sir.
Yeah, that is true, but you will get Avogadro number also, like calculate the Avogadro number also from this Brownian motion. So you will get the Boltzmann constant as well as Avogadro number. So for if you want to determine the value of thing, then you will get Avogadro, both Avogadro number and Boltzmann constant, because if you know the Boltzmann constant, then you will just divide that Boltzmann constant from universal gas constant, that will give you the Avogadro number. So both A and B are the correct answer. Okay. Okay. The last question.
Sir, show me previous one, sir.
Yes.
Sir, once again show me 9th problem, sir.
Yes.
3 minutes.
Yes. Yes. Please.
Okay, sir, you can move.
Okay. Okay. So this problem, this says in an experiment of Brownian motion, the RMS, what RMS stands for? Root mean squared. RMS displacement. So far we have talked about mean squared displacement. Now we have added one thing, root. So root mean squared displacement in the horizontal direction of a minute spherical particle suspended in water was found to be 11 micrometer. So root mean squared displacement means that is root over of average of delta square. So far we are talking about average of delta square. Here RMS displacement means root over of that. That is actually equal to be 11 micrometer over a 30-second time interval, means the tau, time lag value tau, that is 30 seconds at 27 degrees centigrade. So temperature is given, at which the viscosity of water is 10 to the power minus 3 kg per meter second, that is also given. If the universal gas constant is R, 8.32 joule per mole Kelvin, and Avogadro number Na is equal to 6.023 10 to the power 23, calculate the radius of the particle in micron. So you can calculate this thing. I know that. I will give you one hint, and I will be very much happy if you can do this. So we will start from here. Delta square is 2d tau. Now given root over of this thing, what is given? This is given. This is root mean squared displacement, right? This is given. This is 11 micrometer. Now what is the time lag value? Tau. Time lag. This is called time lag or interval. This is 30 second. So we know then this is root over of average delta square, which is root over of 2d tau is equal to 11 micrometer. So 2d tau is equal to x is equal to 121. So then d is 121 divided by 2 times tau, which is 121 divided by 60 micrometer square per second. But that is, so this is the value. Now you know the d, this thing, this is RT divided by 6 pi eta a n a. Now what is R? R value is given 8.32 joule per mole Kelvin. T is 27 degrees centigrade, which is 300 Kelvin. Eta is 10 to the power minus 3, let's say SI unit, and A we have to calculate. So this will be A is equal to RT by 6 pi eta A d n A. What is R? R is 8.32. What is T? T is 300. What is 6 pi? This is 6 pi. Eta is 10 to the power minus 3. D means this one. This is 121 by 60, but this is in micrometer square. Huh? So I have to convert it in the meter square. This will be minus 12. What is D? That is D. Na is 6.023 times 10 to the power 23. So tell me the answer. Do the calculations and tell me the answer. Which is the correct answer? This will be micrometer in. So this will be in meter. The answer will come in meter because I have converted everything is in this thing. So
Sir, option D.
option B is 0.218.
Option D.
D.
109.
Yes,
Yes,
absolutely
sir.
correct. Absolutely correct. You are absolutely correct. So here my answer is coming out to be 1.09 times 10 to the power minus 5 micrometer, and if you take this 109, so sorry, my answer is coming out to be 10 to the power minus 7, and this will be someone is wants to join right now. Okay, so yeah, here this is, so this one, so this, so for my answer is coming out to be, this is 10 to the power minus 5 and minus 6. So this is minus 5, 7, and this is 7. So this is 0.109 micrometer. Okay. So this is the correct answer. If you do the calculations, I have did it, you will get it. Okay. So option D is correct. Then there is no other problem. I will quickly go through the excerpts of this this week's problem solving sessions. So first we have learnt about how motion of the particle, let me open the pointer option. First we have learnt how the motion of the Brownian particle is changing with different thermodynamic variables or macroscopic variables. So the movement is characterized by the displacements. So average displacement is 0. The mean square displacement varies as 2d tau. Tau is time lag value, d is diffusion. So as diffusion coefficient increases, the motion of the particle will be much more enhanced. So we have to talk about how diffusion coefficient changes. So diffusion coefficient is a function of temperature, viscosity, and the radius, which is of the particle, which is size of the particle. So sometimes let me tell you, this A is called hydrodynamic radius of the particle. So now if temperature increases, diffusion increases, so does the motion. If viscosity decreases, diffusion increases, so does the motion. But if radius of the particle or size of the particle uh, uh, decreases, then diffusion coefficient increases, which will increase the motion of the particle. Now here said that which are the largest motion. So we have cancelled these two options C and D, because this will limit the dynamics, because there will be some caging kind of thing. But for option A and option B, there the media in one case is liquid, which is water, in other case which is air. So that depends on the size of the particle and the viscosity. If the product of the viscosity and the size of the particle, in which case it will be larger, there the motion will be lesser. So the greater the this product, the lesser the motion. Okay. Now here we got to know that how Perrin first got a estimation of the Avogadro number from this Brownian motion. He got a estimation around 7.1, which is larger than today's modern accepted value of the Avogadro number. What is the definition of the Avogadro number? Definition of the Avogadro number in today's sense is how many number of carbon molecules, C12 isotope, these carbon atoms are there in 12 gram of C12 isotope. Okay, pure C12 isotope, which is coming out to be 6.023 in 10 to the power 23 number of this thing. So the ratio will be greater than 1. The ratio will be the ratio will be greater than 1. Okay, so now for this thing, what we have seen, so here first they said that pressure has become 1/16 of the pressure at the sea level, and then said if the temperature at that height is increased further 4 times, then how the pressure will change. So first we have seen that according to the gas equation, pressure will be linearly varying with number density. Now number density means how many number of air molecules will be there, that actually follows, their ratio will follows this Boltzmann distribution, where V is are like potential at that height, and if you since this follow number density follows this same distribution, pressure will follow the same distribution. So here in terms of the potential, there will only be the gravitational potential energy. Now what is the gravitational potential energy at Z? That is mgz. And what is the potential at ground? That will be mgz0, and we have put it here. Now P1, which is the pressure at Z, that is pressure, that is 1/16 of the pressure of the sea level P0. So this is P0 by 16. We cancel out P0. So this quantity exponential of minus mg z minus z0 divided by kBt, that comes out to be 1/16. Now if we change the temperature T from T prime, where T prime is 4 times of T, then that P prime will be P0 exponential minus of mg z minus z0 by kb T prime. And if we substitute T prime as 4T, then there will be mg all mg z minus z0 divided by 4 kBt. That is, we have written here 4 kBt. Now we know exponential of minus ab is exponential of minus a to the power b. So that we have done here. We have just taken this 1/4 to here. So this will be 1/4 times mg z minus z0 by kBt. So we have put it here to the power 1/4. So this is exponential of this to the power 1/4, and we know this expression is 1/16. So we put it here 1/16, 1/4 to the power 1/4, that comes to the 2 to the power minus 1. So this pressure will be half. That is we got. So option C is correct answer. Next, the problem says what will be the number density ratio at height. So we know that pressure and number density, they actually linearly proportional. So as pressure becomes 1/8, so number density at height, that will also be 1/8 of number density at base. Okay, and then the problem says what will be the height where the number density falls as 1/e. So we will use this Boltzmann distribution where number density is n at height z and number density is n0 at height z0. We will get the ratio, and this ratio is 1/e, which is nothing but exponential of minus 1. Since this is exponential of minus 1, so from identity we can write mg z minus z0 divided by kBt is equal to 1, which is mg z minus z0 divided by RT. How can we write it? Here small m is the mass of single molecule. We just changed because we know that universal gas constant divided by molar mass divided by Boltzmann constant divided by single molecule mass. Since universal gas constant is Kb times Na, Avogadro number, and molar mass is small m times Na, and we have put it here. Then after that, after doing little bit of algebra, we get this Z0 plus RT by mg. We have written it here. Next, there is a easy problem where we have to calculate the diffusion coefficient, and the displacement at certain interval times are given. The intervals are, the displacement at 30-second intervals are this thing. We calculated the square of these displacements, that is this thing. Then we calculate the average of these square displacements. since there are 11 points, that is 1 by 11 times this summation of this square, we got this. So this is 2 dt, 2 d tau. So d will be this mean square displacement divided by 2 t tau, 2 tau. So this is mean square displacement, this is 2 times tau, tau is 30 second, and we got this diffusion coefficient. Next we got what will be the best description of the Brownian motion, and which comes out to be this option A, where the gas or liquid molecule travels in straight line and until its direction is randomized by a collision with another molecule. Now next problem says that how can we get what we can get from study of Brownian motion. We said that, as Perrin also did, we first can get the Boltzmann constant Kb, then from there we can get Avogadro number, because universal gas constant thing is given, or we know. We will get the ratio of these two things from universal gas constant divided by Boltzmann distribution, Boltzmann constant, and we will get the Avogadro number. And last problem says how to calculate radius of particle of the Brownian particle. We said that mean square displacement is root over of 2 dt. Here root mean square displacement was given, so we will take the root, then we will square it. So mean square displacement is square of that root mean square displacement, and from there we will calculate the d. And since d varies with a, after putting all this expression, we will get the radius of the this thing particle. Okay, so this is this. So I will, if you guys any problem, I will wait for 1 minute for any queries. Okay, if not, then this is the end of this session. We'll see you next Monday. Okay.